So today we're going to take a little side trip. We're going to look at some of the other gas properties that we have. We're going to focus on what they call the kinetic theory of gases. It's just, this was a new theory in around 1877. Not that long ago, honestly. I mean, it's over 100 years ago. But at that point in time in science, they did not believe in atoms or ions or molecules. And Boltzmann was starting to believe in atoms. He was a person who believed in molecules and atoms, and he was trying to determine or do the math behind pressure, temperature, volume, entropy, using this idea of discrete molecules and statistics. So he's the one, Boltzmann is the one who developed this kinetic theory of the gases and talked about molecular velocities and so on. He was completely criticized and hounded by the folks who were of the philosophical school called the positivists. And they said, not that if you can't prove something that you're just lacking in your proof, they said if it can't be proved mathematically, it doesn't exist, which is a really bold philosophical statement. And they went so far to say you can't prove molecules, atoms, ions exist, you can't observe them, so therefore don't even talk about them because you can't prove that they exist. So, we don't believe in them. And Boltzmann was starting to kind of chip away at that and sort of prove that the mathematics of discrete particles actually match the data. So we owe a lot to him. We'll use the atmosphere sort of as our composite gas. So let's learn about our atmosphere as we're talking about these things. And it is a really, really interesting. Here's along the y-axis the altitude of our atmosphere going up to 90 kilometers. And there's several things that are plotted on here. One of them is the pressure. Notice the pressure drops dramatically by the time it gets to 10 kilometers above sea level. The pressure is down to like 0.25 atmosphere, so one quarter. So 75% of the atmosphere is below 10 kilometers. That's the typical height of an airliner. Okay, so when you're flying on an airplane, 80%, maybe 90% of the atmosphere is below you. That's why they fly that high, so that there's less resistance. They provide the fuel and the oxygen. They provide the fuel. The atmosphere provides the oxygen, and they can push that airliner through a very rare gas. I mean, it's not very much pressure up there, so there's not a lot of resistance. They could go higher if they were going faster, and so there are some higher planes. The Concorde, a supersonic airliner, goes higher than that. SR-71 Blackbird goes even higher, and then the NASA X-43A, sort of the experimental plane, goes even further. Okay. Now, atmospheric density also drops down, and then temperature does a really weird thing. Look at the temperature curve. So this is the temperature curve. It drops as you get up there, and then it sort of stops, and then it starts to rise again. Okay, and then it drops again, and then it tapers off. So look at the temperature curve. That's really bizarre. And that's what's also governing sort of where our clouds form. So there's temperature drops, water will condense, and so you'll get clouds forming at different layers along this area in the troposphere. This tropopause, that's where our ozone, where our ozone layer is up here in this stratosphere, around 30 kilometers high. And that ozone layer is what absorbs the deep UV and protects us from the sun's rays. And that absorption of the ozone layer, that's what's causing this temperature rise here. So that sunlight is being absorbed by ozone and other compounds up there and stopping the UV light, and that's causing a rise in temperature. And so Dalton's law applies. So this atmosphere is a complex mixture of gases. It's mostly nitrogen and oxygen. And so we'll use Dalton's law on the next slide to kind of understand something about the composition of the atmosphere. Okay, let's look at this. We have a temperature here. So, up here at sea level, around 300, 298 Kelvin. Notice it drops down to almost 200 Kelvin up here in the upper atmosphere. Definitely below 273, so ice can form. We also have pressure. Now this pressure is listed in kilonewtons per meter squared, so 1,000 newtons per meter squared, and a newton per square meter is a pascal. So again, one atmosphere pressure is right here around 101 kilopascals. So that's the pressure curve here. So we can see that pressure curve here is plotted along this axis. And then we have density, which is mass over volume. And we'll talk about density today. So how do we understand the density of gases? We'll do some problems related to that. And then if we're talking about densities, this density is listed as kilograms per meter cubed. So let's think about kilograms per meter cubed. A kilogram is 1,000 grams, and a meter cubed is 1,000 liters. And so this density unit is also grams per liter. So that's a really convenient term. We deal with things in grams pretty easily in our mind. You know, a liter is a little bit more than this, and so we kind of have an idea of what a liter is. And so this is the size of our atmosphere is absolutely huge. I put a refresher of some of the metric system prefixes over here, just to remind you. We know what kilo is, right? 10 to the 3, 1,000 grams, kilogram. We know that mega is a 10 to the 6th, and giga is 10 to the 9th. Maybe if you're, getting on up into but they use this, it's not exactly the metric system, but you've heard of a terabyte hard drive, right? So that's 10 to the 12. And then we have two more above that. PETA, P-E-T-A, is 10 to the 15th, and exa is E, which is 10 to the 18th. So these are the big parts of the metric system. And in terms of moles of the atmosphere, it's petamoles, okay? So 182,000 petamoles. I could have written 182 examoles, but I wanted to keep it in petamoles because we go down into the single digits and fractions of a petamole down here in these smaller components. But that's how big our atmosphere is in number of moles. So let's write that in scientific notation to practice. So 182,000 petamoles. Okay, 182,000 times 10 to the 15 moles. That's not quite in scientific notation. I need to add some numbers to that 15 if I want to move the decimal place over here. So I can go 15, 16, 17, 18, 19, 20. So it's 1.82 times 10 to the 20 moles. That's how many particles are in the atmosphere of all types: nitrogen, oxygen, CO2, and everything. So 10 to the 20. So it's almost a mole of moles. Okay, take that times 10 to the 23rd, and you've got the number of particles. This is the number of moles of particles. It'd be 1.82 times 6 times 10 to the 43 particles. So it's a lot of particles. In terms of the major components, we have this term X over here. What is that? Well, X is mole fraction. Okay, it's the number of moles of that substance divided by the total number of moles. And so in terms of nitrogen, X equals 0.78. So it's saying of the total number of moles, 78% of those are nitrogen, and 21% of those are oxygen. Notice that doesn't quite add up to 100. That gets up to 99. And so we have 1% argon. So those are the major components. There's three components: nitrogen, oxygen, and argon. That's a good trivia question. You might miss that. Okay. Now that's in dry air. You have to specify dry air because water can be between 1 and 5%. And so water, could be on a really dry area, 1% of the atmosphere; on a really humid area, 5% of the atmosphere. Feels like 50% in Huntsville sometimes, but it's only 5%. Okay. And so that's mole fraction. So the water mole fraction, let's look at the 0.01. That's 0.01 moles of water per mole of atmosphere. That could also be, if you look at, the ideal gas law, moles are proportional to volume. And so you could also say there's 0.01 liters of water in a liter of atmosphere. That would be liters of gaseous water or water vapor. And also pressure. Moles are directly proportional to pressure. And so you could say if you're at 1 atmosphere, the partial pressure of water is 0.01. So 0.01 atmospheres of water in 1 atmosphere pressure of the atmosphere. Yeah. So these are other ways, I guess, to interpret the mole fraction. You could do it by moles, you could do it by volume, you could do it by partial pressure. That's a handy thing. I know you don't know it's handy right now, but it is. You might put a star on this page, okay? Because we deal with mole fractions in the future and in many other courses, and so it's a really helpful thing to think about. Okay. Now, if you wanted to take that 0.01 and convert it to a percent, you just multiply it by 100%. And so that would be 1%. And you could do V over V, which to show you that's volume percent. Most of the time, your percentages are either V over V or volume percent or M over M, which is mass percent. Okay. We're not going to use mass percent on this page. We're going to run out of room. But it would be the mass of water divided by the mass of the atmosphere. Okay. And so we've got that over here. We could figure that out. It'd be this 32.8 divided by the 5,270. Okay. And that would be the percent. Let's just do that just real quick since we brought it up. So mass percent, let's take 32,800 divided by 5,270. Okay, someone with a calculator, can you knock that one out? 32,800 divided by 5,270,000. 0.0062. Okay. 0.0062. Okay.
Does that say 55%?
This says mass percent. Yeah. Thanks for clarifying. So mass percent of water. And so it's 0.0062, so it's not quite 0.01. It's different. It's not dramatically different in this example, but it's different. So that's why whenever you give a percent, you need to specify how did you calculate that percent. Was that a volume percent? Was that a mass percent or a mole percent? Okay. Now let's look at CO2. Notice the mole fraction is 0.000415. If we made that into percent, it really wouldn't help. It'd still be 0.04%. And that the whole idea of changing the sort of the basis of the number is to get to a number that's easy to write, easy to communicate. And so in this case, instead of multiplying by 100%, notice this has two pieces, 100%. What are we actually multiplying by? We're multiplying by 100, and this percent means 1 over 100. So we're just multiplying by 1. And instead of writing this percent piece, per century, we're just using the symbol. Does that make sense? Yeah. So that seems overly simplistic, right, to explain, but it really helps when doing the next one. Here we're multiplying by 10 to the 6th ppm. What is ppm? It's parts per million. It's part per 10 to the 6th. So once again, we're just multiplying by 1 in general, but we're changing the units. And instead of writing this 1 over 10 to the 6th, we write the symbol for that, which is ppm, parts per million. And so this, if we move that decimal place 6 places, we end up with 415 parts per million. VV, so by volume or mole percent, or by mole, you would say. So 415 parts per million by mole or volume would be the concentration of CO2 in the atmosphere. So now you understand when I talk about CO2 concentrations in terms of parts per million, how do we get out of parts per million and back to mole fraction? we would then just divide that by 10 to the 6th ppm, and the ppms cancel, and we end up with 415 times 10 to the minus 6, or this number up above. Okay. So that's a really important skill. You'll learn that you'll use that in analytical. You'll use that in other places, quant and instrumental. Okay. So let's ask a general question. Why do helium balloons float? You know, you go to a birthday party, you want to see a balloon. You want it to float, not be on the floor. Okay.
So it's lighter in there?
Yeah, so it's the density, right? The density of the atmosphere is such, and then the helium has a less density than that. So let's figure out what we do with density. So let's combine density and the ideal gas law. So we know that density is mass over volume. And we know the ideal gas law, PV equals nRT. And we know that the number of moles is the mass of a substance divided by its molar mass, right? So if we take a particular mass, let's say we have 5 grams of O2, how will we know how many moles we have? We divide by 32 grams of O2 per mole, and that gives us the moles, okay? What's 5 over 32? I should have picked easier numbers. How about 8 over 32? Make that an 8. Okay. What is that, 0.25 now? Very good. So we got a quarter of a mole of oxygen. Okay. So yeah, so we're good with this. Mass over molar mass is the number of moles. We've got the PV equals nRT, and we know the definition of density is mass over volume. So let's put this piece in. This piece right here, let's put that in for this. So PV is equal to the mass I have over the molar mass, or molecular weight, if you want to call it that, RT. Now I have a volume in here and I have a mass in here. So let's move the volume over to the right and everything else over to the left, okay? And so I'm going to say P times the molar mass over RT is equal to mass over volume. Did everybody follow the algebra there? I moved this molar mass over to the other side. It's in the denominator, so it'll be in the numerator over there. These things are in the numerator, so they'll be in the denominator when I move them to the other side. And then I have a volume over here in the denominator. So this is equal to the density. So the density is equal to the pressure times the molar mass divided by RT. This is another great way to figure out what the molar mass is of a gas. So if I could measure the density of a gas and its temperature and its pressure, then I would know the molar mass of the particles in there. And that's pretty neat. That's how they determined a lot of the molar masses of the gaseous substances. So they would collect the gas with the water displacement. They would correct for the water. They know the volume. They could take that evacuated cell and weigh it, and then they could weigh it with the gas in there, and they could figure out what that density was. So now we have an idea of this density. If we have the molar mass, we have the pressure, the temperature, the ideal gas law, we could figure out what the density of a gas is. So how high will a helium balloon go? We have the density of our atmosphere here. What's the density of helium at STP? Okay. So the STP part tells us what the pressure will be. So we know that. We know the temperature, we know the gas constant, we know the molar mass of helium. We can look that up on the periodic table. It's going to be 4 grams per mole. Okay. And so we have 1 atmosphere, 4 grams per mole for the helium, our gas constant, the per moles cancel, standard temperature, the kelvins cancel, standard pressure, the atmospheres cancel, and I have a density grams per liter. Okay. And so at 0.18 grams per liter. And so it's going to want to climb until this, remember this was kilograms per meters cubed, which was also grams per liter. So that helium balloon is going to follow this density curve up here until we get to 0.18, which is about 0.2. So this is 0.5432. So it's going to climb up to right here, about 15 kilometers high. That's pretty cool. Okay. So 15, 20 kilometers. When we get down that far, let's see, 0.18. Yeah. When we get down that far, what's the pressure done? The pressure has changed. What's the temperature done? Well, the temperature has changed. We're no longer at STP. Okay. So let's put in the new temperature and the new pressure. Okay, we're down here at around 10 kilopascals. Okay. So 10 kilopascals, that's not a very convenient unit. So let's go ahead and convert that to atmospheres. 101 kilopascals per atmosphere. That was on the last page of the notes, in the previous set of notes. Same molar mass for helium. Now we're at a colder temperature. We're around 220 Kelvin. Kelvin cancels, per mole cancel, kilopascals have canceled, atmospheres have canceled. Notice if I use the units, I know I got it right, or at least I got the correct arrangement of all of the numbers. So our density is going to change. So now it's 0.022 grams per liter. So it's going to be way down here. It's going to get on up to 0.0 something. It's going to be up here around 35, 40 kilometers. And sure enough, look here, we have weather balloon. So that helium balloon is going to climb and climb and climb until the density matches the density of the atmosphere. And so it keeps going until actually what happens is eventually the volume won't increase anymore because you reach the limits of the bag that it's in, and it'll stop and it'll fix the density. So it won't keep climbing forever. It'll reach a minimum density, and then that's where it will stop.
Are we running out of helium?
Good question. Okay, so helium comes from radioactive decay in the Earth's crust. Whenever you have radioactive decay, alpha particles, especially the heavy elements, give off alpha particles. Those alpha particles are helium nuclei. They quickly grab 2 electrons to become helium, and now you have a noble gas dissolved in rock. So it percolates out, and it's going to go in places where there's caverns, canyons, or porous rock formations like sand. And so there are places where we have helium mines, where you can go down, you have natural gas, but you also have a lot of helium. A lot of places they will separate that helium from the natural gas and pump the helium back down into a rock formation for safekeeping. There was a facility in Amarillo. This is why I know about this, because there was a government helium repository. It was run by the U.S. government, and it had just an enormous amount of helium pumped into an underground rock formation, essentially, and they could pull it out as we needed it. Yes. This conversion factor here? Yes. Okay. So this is one of the definitional conversion factors from the last set of notes on the back page. It says other pressure conversions, and PSI and everything like that. Yeah. And so the helium switched. They went from a government facility to a private contractor, and there was a blip in the contracts, and CERN in Switzerland didn't have their contracts with this new group, and they couldn't get helium, and it started this panic that we were going to run out of helium. So we're not close to running out of helium, but it is a limited resource because it percolates out of those rocks so slowly. Okay, we're not going to quote run out, but getting it out of the ground is going to get more difficult. So we have a lot, but it's not going to last forever, right? So it's a complicated answer.
40 years?
Probably more than that.
Okay.
Yeah, we're good then. But if we wanted to have magnetic levitation and superconducting trains, then we probably wouldn't have enough for that. That would cause our consumption of helium to go up. So let's compare gases and liquid densities. Liquid water has a density of 1 gram per mil. Okay. So memorize that number. It will do you well. 1 gram per milliliter or 1 gram per cubic centimeter, which is the same thing, cc. And this is a liquid density. So let's compare that to the gas densities. So what's the density of water vapor at STP? So here's our density equation. We put in, instead of the molar mass of 4 for helium, we have 18 for water, so 18 grams per mole. Again, we know that we did this problem correct because of all of our units canceling. And so 0.8, it looks like it's close to the density of water, but it's not. It's not milliliters, that's for a liter. So it's 0.8 grams per liter. So liquid water is 1,000 times more dense than gaseous water. And that's a nice rule of thumb, that gases take up 1,000 times more space than liquids and solids. So if you have something that goes to a gas, it's going to expand about 1,000 times. And that's why explosives do so much damage. So you have a solid explosive and you detonate it and you create a lot of gaseous products. So if you had an explosive that takes up 1 liter of volume as a solid, you have an explosion, and now if all those molecules just went to 1 mole, from 1 mole of solid to 1 mole of gas, it would expand 1,000 times. If you created 8 moles of gas, it'd be 8,000 times. Okay. If you raise the temperature, it's going to expand even more because hot gases take up even more space. So that's this whole reason why we use explosives to break rock and all kinds of things in mining, is that we want to have this shock of this expansion and it breaks things. Now, bad guys want to break things that we want to use and break people, but we use explosives in mining all the time. And that's how we mine all of our precious metals, all of our battery components and everything, is you can sit there with the jackhammer and tap at it. Or you can drill a little hole, put some explosives in there and fracture the whole rock face and then scoop it up and separate the minerals that you need. So, now, what is this ratio of gas to liquid densities? Let's just look at that. So yeah, water, that ratio is 1,200. So liquid or vapor, water vapor, takes up 1,200 times the space of liquid water. Let's see what it does for gasoline, like octane. I just picked an octane out of the blue. C8H18 is the molecular formula. And here's the liquid density. You don't have to memorize the liquid densities of hydrocarbons, but they're all less than water. That's why they float. The light hydrocarbons, oil floats on top of water, unless it's a really, really heavy oil. And so here we have this molar mass added up. We have 8 carbon atoms times 12 grams per mole of each, and then 18 hydrogens. Okay, these from the periodic table. And this 8 right here is the number of carbons, and this 18 is the number of hydrogens. So that's where I got the molar mass for octane. The rest of the things you ought to recognize. And so this is the vapor density of octane, 5.1 grams per liter. Much more dense than water, isn't it?
So I have a question.
Yes.
So even if to get to that state of water vapor, it has to be heated, but if it says STP, we just always use 273.
Yeah, it's kind of if it's at STP, we use 270. Like you have to boil the water, right, at 373 Kelvin. So it's 100 Celsius, so 100 plus 273. So 373 Kelvin would be the boiling point of water. You boil that up, and then you take that container that has the vapor in it, and you cool it down to STP. And a lot of these things are just mathematical comparisons. Like in reality, that water would start to condense on the side of the container because it's below its boiling point, right? But this would be the density at STP of water, okay? Even though it'd be hard to get it to STP without it condensing. Does that make sense? So we can do things mathematically that don't make a lot of sense in the real world, right? And STP is one of those, taking something that's going to condense and talking about it at STP, but it helps us compare apples and apples, everything at the same temperature and the same pressure. Does that make sense?
Yeah.
But you're right to be kind of, your little brain's, sparking on that. You're like, wait, water would be a vapor at higher temperature, not at STP. Now there is water vapor at it's the vapor pressure at room temperature, or at even 0 C. And so that particular vapor pressure, that the density of that water at that vapor pressure would still be this density, 0.8. Now, one thing I want to show, notice how much more dense the octane is than the water. And so we can see from this equation here that density is proportional to the molar mass. Okay? And so if you were to be given 5 molecules and say, which one of these has the most dense vapor? Just pick the heaviest one. You got more mass in the same container, so it's going to be more dense. Make sense? So density goes up as molar mass goes up. And here octane has a huge molar mass, and so it has a huge density compared to water. Okay, so this ratio of liquid gas to liquid, let's see. Yeah, liquid to gas densities would be 138. And so that's just that gas taking up only 138 times the space of the liquid for octane. Okay, so this is a practical example of expanding vapor. This is a boiling liquid expanding vapor explosion. I'm going to stop the video so that I don't get a copyright strike. No, let's see. We'll risk it. If I get a strike, then I'll. You'll see. Okay.
It's a blackboard. It's all good.
Yeah, that's true. It's blackboard. Okay, what'd you say now?
Oh, nothing. I just wanted to get that 138.
Okay, sure. Yeah. Got it? Okay, so let's look at this.
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure.
You see that up there? That's shooting out and burning
As
way up
pressure
there.
decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature.
Y'all ever boil water in a paper cup? Same thing, right? The liquid on the other side of the paper is keeping the paper from catching fire. Next time you're on a camp out, get you a paper cup, put some water in it, set it right on the coals, and the water will boil and the cup will just sit there.
Oh, wow.
Now, if it's a plastic cup, yeah, it'll melt. But get a paper cup, like a real paper cup. If you don't have one, get a piece of notebook paper and fold it into like a hat. Pour water in it and set it in the coals. Be careful with the setting it in the coals part. Yeah. Now, it'll burn around the top, but the liquid will keep that paper at the boiling point of the liquid. And paper doesn't burn at the boiling point of the liquid. So all the joules go right through the paper and into the liquid. And that's what's happening here. It's protecting the tank. But when that liquid gets below, too low, then the tank gets
With
weak.
continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause
I wanted to see the shock wave.
are released as the tank and eventually tear.
Did you see the shock wave, the spherical shock wave shootout? Anyway, that's the expanding pressure wave of the gas. It's just shooting out. Okay.
As the tank comes apart,
Okay, so molecular velocities. How fast are those molecules going? Well, Boltzmann determined that the kinetic energy of a gas was 3/2 RT. And Newton also had a kinetic energy equation. If you're throwing a baseball, what is the kinetic energy? 1/2 mv squared. Mass of the ball, how fast you can throw, that's the kinetic energy of the baseball. So if we set these equal to each other, we can solve for the velocity of the gas. Okay, so we have the velocity of the gas's molar mass. We have the velocity, 1/2 mv squared. That's Newton's kinetic energy. And Boltzmann's kinetic energy is 3/2 RT for translational velocity of a monatomic gas, something like a single atom. And so the 1/2s cancel, so the 2's are gone. We move the molar mass over to the other side and take the square root. And so the velocity of a gas, and this happens to be the root mean squared velocity of the gas, is the square root of 3RT over m. And so that's what's going on with our gas containers and our pressure. It's the collision of those gas molecules against the walls of the container that create the pressure. Okay. And if you take a square, meter of that, there's 1 Pascal is a Newton of force. So those molecules hitting that wall with a Newton of force in a square meter, that's 1 Pascal. Okay. For 1 atmosphere, it's 101,325 newtons of force per square meter. And then this is the molecular weight dependence. So the smallest molar mass, so H2, that's going to be the fastest velocities. And this RMS value is going to be a value just past the maximum value. So right about here, that would be this value here, V. Now notice it's a single number that's supposed to represent this distribution of velocities, because in a gas you've got some slow molecules and some really fast molecules. And so this is like an average value. It's not exactly the average, it's called the root mean squared value. And this would be the helium value, so as you increase the mass, the velocities on average get smaller. And the water, and nitrogen and oxygen. And so these heavy molecules aren't moving as fast as the lighter molecules. Now Graham came up with this idea that he said that the amount of molecules that leave a pinhole, so here's a bunch of molecules, the amount of molecules that leave the pinhole is proportional to this velocity. So amount of molecules, that sounds like a number of moles in a given time. That's the effusion rate, is proportional to velocity. And so we have this moles of gas per time is proportional to the velocity of that gas. And so here's a mole of another gas is equal to that velocity. So we can have this, again, anytime you have a proportionality, if you put numbers on there, we can put ones and twos on the time as well, then you can make an equal sign. And so this is a great way to use Graham's law of effusion. So if we put this together with the velocity equation, then we can have ones and twos on everything, including the times. Okay. Notice this is not as simple as the PV equals nRT governing equation that I wrote on the top of the board over there, because of that square root. Okay, so you have to take into account the square root. That's the number one place where people mess this up. It's not a direct relationship with the temperature, it's a square root relationship to the temperature. And it's not a direct relationship with the mass, it's a square root relationship. So we'll do some problems related to that. So calculate the rate of effusion of hydrogen to the rate of effusion of oxygen. So we want this ratio. Here's our rate of effusion for hydrogen, and here's our rate of effusion for oxygen, and here's our velocities. And so what we have is the gas constant is the same, the 3 is the same. We're talking about the same temperature. It doesn't say anything in the problem about temperature, so we'll just assume that the temperature is the same. And so we need to simplify this equation now. I'm going to do it in 2 steps. So we end up with 1 over the molar mass of hydrogen under the square root divided by 1 over the molar mass of O2. So how can we simplify this? Well, we can put the square root over everything. Okay. And this 1 over mass of oxygen, that means it comes to the top. So the mass of O2 is on top and the mass of hydrogen is on bottom. Okay, so my grams per mole cancel, and I have 32 divided by 2, which is 16, but you got to take the square root. The square root of 16 is equal to 4. Okay. So that means hydrogen So if I have a hydrogen tank and I have a tiny pinhole leak, hydrogen will come out of that same pinhole 4 times faster than oxygen. Yes?
So why can't the square root cancel out?
Because they're an operator. You're taking the square root of something. It's not a number. Yeah, so it's an operator. It's a good question. He said, why didn't the square roots cancel since they're on top and bottom? But the square root is an operator. It's a function you're doing to a number, and it's not a number. Yes?
Why did the H2 go to the bottom and the O2 go to the top?
Yeah, so essentially it'd be like, let me write over here, 1 over A divided by 1 over B. That B is going to come all the way to the top. So it's going to be B over A. Yeah, same kind of thing. Only we just did it all inside the square root. So it was as if we weren't paying attention to the square roots. We just moved that MO2 up to the top. Excellent. Okay. We have enough time for the last problem here. Some cars use liquid natural gas as a fuel, which is mostly methane. If a car's tank of methane leaks at the small rate of 1 mole per day, how long would it take for 1 mole of hydrogen to leak from this tank if we ran the car on hydrogen? Okay, so that's the word problem. Here's our overall equation. Okay, time, we're going to say temperature is unchanged, the gas constant's unchanged, 3 is unchanged. We've got the mass of hydrogen and mass of methane. Okay, we've got 1 mole of methane. So this is 1 mole here, 1 mole. And it's saying how long would it take for 1 mole of hydrogen to leak too? So this is also 1 mole. So my ends have canceled. And the only 2 variables I have are the times and the molar masses. And so this one is 1 over TH2 over 1 over T CH4. This is the side that people mess up on these kinds of problems. And this is, I'm going to write it out, 1 over MH2 over 1 over MCH4 under the square root. Okay. So we got a lot of 1/overs. So I wanted you to have some practice on that. So this CH4 comes all the way to the top. So this is the time for CH4 over the time for hydrogen is equal to the mass of CH4 over the mass of hydrogen, all under the square root. Okay, I know all of the 3 out of the 4 of these numbers. So the time it takes for methane to leak out, and this was 1 day for the hydrogen. That was the time for the hydrogen. Okay, I had to stop the video and go back because right at 10 till, right at the end of class, I discovered that when I put the numbers in for this problem, I had done the algebra right, but I put the 1 day on the wrong side. So the known up here is that methane leaks out at 1 mole per day. And so this is actually 1 day right here. Right here, 1 day. And this is the unknown, the time it takes for the hydrogen to leak out. So we actually have to redo some of this algebra to get our variable on the left and to get our constants on the right. And so I'm going to redo that here. Let me switch views. Okay, so we have that same equation where all of these different things cancel out. The temperature is the same. Okay, for both the gas constant, etc., R and 3. We have the number of moles, which is 1 mole is the same, and so we have this simplified equation. The time it takes for methane to leak out divided by the time it takes for hydrogen to leak out is equal to the square root of the molar mass ratio. So you can see that the 1 over methane, the time has come up to the top. Same thing for the mass. Okay, this 1 over the methane mass has come to the top. So we have this equation here, and we want to solve for the time it takes the hydrogen to leak out. And so this is the equation. This looks very similar to what we had before, but these masses over here are opposite. They've been flipped. Okay, and so we put in our variables. We know that the time it takes for methane to leak is 1 day for 1 mole. And we have the molar masses, 2 over 16, so that's 1/8, and we take the square root of that. So it takes the square root of 1/8 of a day for this same amount of hydrogen to leak out. And so it would be 0.35 days, or about 8.5 hours. I knew that I had made a mistake because I knew the hydrogen would leak out faster. And when I got to that last problem at the end of class, I noticed that my result said that it would leak out in the square root of 8 days. Well, square root of 8 is the square root of 4 times 2, and the square root of 4 is 2, so it would be 2 times the square root of 2. I knew that was greater than 1. I knew that this was going to be coming out slower, and I knew that couldn't be right. And so that was the clue that I got, but it was too late to do this in class. So hopefully this cleared things up, and also this does I did what I want you to do, and that is when you finish the problem, look at the result and see if it makes sense. Okay, this is greater than 1 day. And methane came out 1 mole in 1 day, and hydrogen is lighter. It's going to leak out faster. And so this should have been less than 1 day. So I knew that I had a mistake, and I had just put my variable on the wrong side. Okay, so go through this again if you want to, and check my algebra, check my math, and I think you'll see that it works this time. All right, sorry for the mistake. We're running up against the clock, and I just put the 1 day on the wrong side of that equation. All right, yeah, have a great day. Or did I do this wrong? I should have solved. I was trying to solve for the time of hydrogen, not the time of methane. Oh goodness, we're out of time. I'll finish it on a video. I just, that last mistake, I solved for the time of methane, not the time of hydrogen. Got those two switched.